Hello, AP Chemistry. So we are still on Unit 3. This is part 4 of the 5-part series on Unit 3, biggest unit in the AP curriculum. All right, so in this video, we are going to look at solutions. All right, so solutions should be a pretty simple topic. Interactions between intermolecular forces influence the solubility and separation of mixtures. So again, our iconic view of a solution, we have the solvent, typically water, but not always, and the solute dispersed around it. The AP curriculum really wants to distinguish that when we talk about solutions, these are homogeneous mixtures, right? Something like a heterogeneous mixture, we would have large particulate. All right, so solution composition, it can be expressed in a variety of ways. All of those compositions we would call concentration. All right, so different ways to talk about the concentration of a solution. The one we are going to use is molarity. There's also molality, mass percent or percent by mass, percent by volume, parts per million, parts per billion, mole fraction. But for solutions, specifically our liquid solutions, we are always going to use molarity. That is the moles of solute divided by liters of solution. And this is my favorite picture, 2 moles per liter. I really think that, you know, when the AP exam is over, we should all get these shirts. I think that'd be a really nice idea. But moles per liter, something we've seen several times. All right, a big thing just to remember, all right, moles per liter can be pretty simple, but our ionic compounds, when they dissolve, all right, the ions dissociate, they separate, right, if it's soluble. So something like calcium chloride, definitely soluble, it's going to separate. So just remember, in solution, calcium chloride is going to be, for every 1 calcium ion in the solution, you will have 2 chloride ions. All right, so if you had a 1 molar calcium chloride solution, that means you have a 1 molar calcium solution, the Ca2+, but you have a 2 molar chloride solution. All right, so you can use those like stoichiometric coefficients. So because CaCl2 separates, you have 1 part calcium and 2 parts chloride. So if you had a 1 molar calcium chloride, again, 1 molar calcium, 2 molars chloride. All right, same thing if it was 0.5, you would be 0.5 and 1. You would just double it for the chloride because you're getting 2 of them per every 1 mole. All right, and another thing, dilution is an important concept with solutions. All right, so we typically write it out as M1V1 equals M2V2. I've seen the AP curriculum write it out as C1V1 equals C2V2. The C, they're just saying it's concentration. That shouldn't really throw us off for too much. If we look at the particle diagrams, though, we're adding more water, so we're spreading out the solute more. All right, we're never adding more moles. We're just adding more water, so the concentration always goes down, the molarity goes down. One thing to keep in mind, concentration times volume or molarity times volume always gives you moles, right? So in this equation, it's just saying moles equals moles. All right, now, one last thing I want to mention, the solution composition. While we typically think of it for the liquid phase, it can be for a gas. All right, so we know that we write our concentrations, we write our molarities in brackets, and we will see that especially in like equilibrium, sometimes in reaction rate, we're looking at molarities in some of those pieces, and it could be for a gas, right? So the solution composition, it can be for a gas. We can think about the moles of gas in a given volume of space, all right? So that will also give us the molarity. It can be for the gas phase, and it can be for a solid. It's not often, but it can be for those other 2 phases. All right, now the AP curriculum, it really likes these particulate representations of solutions. All right, it's going to communicate the structure and properties of the solutions, and the illustrations are going to show relative concentrations of the components in the solution. So these pictures are from previous AP exams. All right, here we have 2 figures. We have the key, right? So they're going to give you that key. They're going to give you the figures. We should be able to tell that figure 2 has more of the H3O, for example, right? They're going to give you this. These will be prompts. We should feel comfortable with reading these particle representations, all right? And there will be some very subtle details. So here's another picture from a previous AP free response question, all right? Now, I just want to think relative concentrations. We see that there's the solid, but if we look at it, they're being very intentional, the AP, with putting 2 Na ions and 4 NO3 ions, right? So maybe there's a reaction that produced this or something else going on. Maybe it was, I don't know, whatever they're doing, they're very intentional with the number they draw, and you're gonna wanna think through that when you answer any questions showing a particle diagram of a solution, all right? Nothing is an accident in these pictures. So the calcium probably was with the nitrate, which is why there's twice as much of it, because that's CaNO3 too, right? So something like that will show up in these questions. So again, don't take anything for granted. Everything is in there for a very specific reason. Relative concentrations is always something that they're showing in these diagrams. All right, and here's just another example. We were seeing that more NaOH is being added. We can think of this in like an acid-base type reaction. Just again, if you look through any one of these, they are specifically showing you something, right? So we have these H3Os, and then we get less of them from drawing to drawing. So that's important. They're doing that on purpose. So have kind of an eye for detail when you see these particle diagrams. All right. Now, the College Board goes out of their way to say that colligative properties are not assessed. All right. But I do believe there's a little bit of an asterisk with that. I think what they're saying is you won't have to do a freezing point depression or a boiling point elevation calculation. All right. They say that calculations of percent by mass, percent by volume, and molality are not necessary. Now, for that freezing point depression and for that boiling point elevation, those two calculations require molality. You might remember those equations are pretty straightforward, though. But what I do want to draw your attention to, if we look at this phase change diagram, which phase change diagrams are another thing the College Board says are not assessed on the AP exam, but they do assume you know them, right? So they might kind of assume that you understand the basics of colligative properties. They're kind of taking it off because they're saying it's too easy. I just want to draw your attention to the vapor pressure, because this is something I feel like the AP, I feel like their current curriculum really likes vapor pressure. All right. For the pure solvent, right, we see its liquid phase and we see where it's in equilibrium at 1 atmosphere. So that's where it changes from liquid to solid. And here's where it changes from liquid to gas. When we have the solution, what the presence of the solution does is it lowers the vapor pressure. Now, as a result of the vapor pressure being lowered, boiling occurs at a higher temperature and freezing at a lower temperature. All right. So just something to remember, the vapor pressure is when we are boiling. When we're boiling, the vapor pressure is equal to atmospheric pressure. So when particles are able to leave the liquid phase and go into the gas phase, right, that is the vapor pressure. It happens at every temperature, right? That's why when we're doing like a gas collection lab, we get partial pressure of water inside of our collected gas, right? That's just its vapor pressure. And at every temperature, there's a given vapor pressure. But when we have a solution, all right, when we have a solution, those particles, right, whether it is sugar in this example, or specifically like if it's ionic, that's going to be even more powerful. But those solute particles that are dissolved, they give the water molecules in the solvent something to be attracted to, all right? So they kind of go near them, and as a result, we get less water molecules leaving the liquid phase and going into the gas phase. So this picture right here really shows what I mean when I say that the solution has a lower vapor pressure. All right, and again, since boiling is when the vapor pressure equals atmospheric pressure, just keep in mind, substances with low vapor pressures have really high boiling points. Substances with high vapor pressures have really low boiling points, right? If it has a high vapor pressure, it will equal atmospheric pressure easier. All right, and then if it has a low vapor pressure, we're going to have to really heat it up before that vapor pressure changes, and it will equal atmospheric pressure. All right, so again, they say that colligative properties are not assessed, but I do think it's important you have this piece about vapor pressure, because I feel like vapor pressure comes up a lot. And again, it's not assessed because it's not being assessed, but they do assume you know it. All right, and again, one last thing, keep in mind what we saw in that molarity example a couple slides ago with the calcium chloride, with the chloride having twice the concentration. That's like the Van Hoff factor. All right, I do believe that the Van Hoff factor kind of shows up from time to time, just the number of particles when something dissolves. All right, and then again, molarity, we are always using molarity. You don't have to do molality. Mole fraction still shows up in our gases. We've seen that in the past, right? We know that with the partial pressures, Dalton's law of partial pressures, we can multiply the mole fraction of a gas by the total pressure to get its partial pressure. So mole fraction does show up. And again, we're not going to use the percent by mass either, or percent by volume. All right, but again, I feel like we do get percentages a lot, especially in like our acid base and our equilibrium, getting the percentage of how much something dissociates. So we do have to feel comfortable with using a percent. It's just part divided by total times 100. So it's nothing too crazy, any of these percentages, but they're saying, again, we're always going to use molarity. All right, now the components of a liquid cannot be separated by filtration. All right, filtration works for a heterogeneous mixture where we have large particles. Right, so it's not evenly mixed throughout. It is not homogeneous, and we get the liquid to come out, and our solid stays behind. All right, that was something at the beginning of the school year. We were doing filtration because we cared about the solid. We wanted all of the liquid to go through. But here we're trying to think, how can we separate the parts of a liquid? All right, and we're going to do something that's going to take advantage of the differences in the intermolecular interactions of the components. That's how we will separate a liquid solution. So two ways to do it. The first way is chromatography. All right, we can do paper chromatography, thin layer or column. In all of these versions, all right, we have some type of unknown and we allow it to move through a solvent. All right, so chromatography separates chemical species by taking advantage of the differential strength of intermolecular interactions between and among the components of the solution, the mobile phase, and with the surface components of the stationary phase. So in our paper chromatography, the paper itself is the stationary phase. All right, we can use paper that is very polar. We can use paper that is very nonpolar. All right, then we dip the paper into a solvent. The solvent is the mobile phase. All right, and the solvent moves upward, right? Capillary action, the solvent moves through the paper. The solvent front is how high the solvent has moved. And if a particular dye or something in the liquid mixture, if something in the liquid mixture is attracted to the solvent, it will move up more with it. If it's more attracted to the stationary phase, the paper itself, it will stay further to the bottom, right? And how high it moves relative to the solvent front, we call the RF, right? The RF factor, it's the retention factor. So again, the components of the solution and with the surface components of the stationary phase, right, how they move. This picture here is directly from, I know it's a little blurry, but it's directly from an old AP free response question. Something that they make a note of, and again, everything is deliberate. They're mentioning that it is a non-polar solvent. We usually expect the solvent to be polar. All right, so whichever dye moves up the most means that it's staying with the nonpolar solvent. So dye C, for example, would be the most nonpolar, right? Because it moved the most with the nonpolar solvent front. And again, unknowns always have the same RF. They might move different heights based on the height of the solvent front, but they always have the same RF. Here in this example, they make it kind of easy because the unknown has moved about halfway. So its RF would be about 0.5 and it lines up with dye A. All right, so again, we've seen paper chromatography. It's pretty simple. Just make sure you check if the solvent is polar or non-polar. They typically won't mention the paper itself, but they might. If they do, that is very intentional. So keep an eye out for that. All right. The other thing is distillation. Distillation separates chemical species by taking advantage of the differential strength of intermolecular attractions between and among the components and the effects these interactions have on the vapor pressures of the components in the mixture. Now, because they are mentioning the vapor pressures, what they're really saying is boiling point. All right. So the idea is you have a solution and it has two different parts, three, four, however many. Let's just assume two. Let's keep it simple. And you add heat. How much heat do you add? You add just enough heat to get one of these substances to boil, but not the other. Right? So let's say that you have something mixed with water. Now, water we know boils at 100 degrees C. Let's say the other liquid boils at 75 degrees C. If we can heat this solution to 80 degrees, the water will not boil. It does not have enough energy, but that other part will, right? It's getting more than enough energy. So you'll get a vapor that boils off, whereas some solution stays behind. And that vapor will rise up on its own, right? The gas will spread out. And when it comes near the top, you have a condenser, and that is going to be an area that's going to be kept cold. Typically, we run water. The low way of setting up a distillation is you just wrap a wet paper towel around it. The idea though is you have this arm coming off where the gas can condense. It'll be colder, it'll condense, and so you'll get these droplets of, we call it the distillate, but it's one of the components of the solution. So you heat it up so it boils, it rises up, and then it recondenses. And again, one of the parts of the solution will stay behind the whole time. All right, so you're taking advantage of their boiling points. And if you ever get the chance to do one of these in a lab, if you take organic chemistry, it's a pretty common lab. It is a very boring lab. I remember doing it years ago on my birthday, actually, and you just count drop by drop. And I was hoping to get out early to celebrate my birthday, and we were in that lab for like 5 hours, and like, again, just drop, drop, drop. Very boring process. Again, if we're looking at these three different components, it's typically used distillation in organic chemistry. Boiling points of 118 degrees C, 56.5 degrees C, and -7 degrees C. All right. We can, if you had a mixture of any two of these, you would use those boiling points to figure out where you would want to set your distillation. So let's say you had these two components on the left, 118 and 56.5. You would want any temperature above 56.5 degrees Celsius, but not at 118, right? So this molecule would boil and this molecule would just stay behind. All right, so that's the point of a distillation. All right, and the last thing, substances with similar intermolecular interactions tend to be miscible or soluble in one another. All right, so think about oil and water. This is a classic example. They don't mix. The oil is nonpolar, the water is polar, and the phrase that everyone knows is like dissolves like. Now, because that is such a common phrase, the College Board doesn't like hearing it anymore. All right, they feel like if you say like dissolves like, that doesn't mean that you truly know what's going on. It just means you know the phrase that everyone knows. So be careful. You do not want to use like dissolves like. It explains what's happening. Molecules dissolve in a solvent with like intermolecular forces, but just specifically state what those intermolecular forces are. All right, so if you want to say something is in the water phase, say, you know, a polar molecule is dissolved in the polar solvent water. All right, here is an example where iodine will stay in a non-polar solvent. And so we'll see that dramatic change in color, right? And based on the solvents, we still have the effects of density, right? So the more dense of the two will still be on the bottom, right? We can use different solvents. I know we're used to water as the universal solvent, right? But there are other ones. Acetone is a common one. Carbon tetrachloride is a common non-polar solvent. You'll see that in a lot of questions. All right, so just be on the lookout for that. Don't just say like dissolves like, mention their intermolecular forces. All right, so the do's when answering questions, excuse me, this shouldn't be gases, this should be on solutions, I apologize. The do's: mention polar or nonpolar when talking about solubility. A nonpolar molecule dissolves in a nonpolar solvent. Don't just say like dissolves like, mention their intermolecular forces. Use M1V1 equals M2V2 for dilution. I'm going to make a prediction now that you will have to do one dilution at some point in the free response on the AP exam, all right? So it's gonna be there somewhere. Assume any volume when given a standard solution, all right? Because the concentration of a solution is the same throughout the solution, if they give you, let's say, a question where they're talking about a 2 molar solution, it's 2 molar whether you're using 50 mLs of it or 100 mLs of it, however much, right? If you start adding water, then you're diluting. But anytime you see questions where it's like a lab scenario and there is just a standard solution, right, with the standard molarity, that molarity is the same no matter what volume you have of it, especially if that volume is not mentioned. It means you can use any volume for that problem. All right, and remember, low vapor pressure means high boiling point. And in those in those colligative properties, the solution always has a lower vapor pressure, right? Which is why it always has that higher boiling point. But just be attuned to vapor pressure. Don't be intimidated by vapor pressure because it's very common in the AP curriculum. All right, the don'ts on solutions. Don't just say like dissolves like, right? That is not enough. They will not give you credit. Don't use any concentration besides molarity, okay? Don't try to be fancy and use something different. Don't forget to adjust the molarity of an ion, all right? So think about the subscripts of an ion. That's gonna be important when it dissociates in the solution. Don't forget a gas or solid can be a solution, all right? Sometimes people kind of get tripped up by that. Don't forget to check if the mobile phase is polar or nonpolar. That's for a paper chromatography question. All right, we assume it's usually going to be polar, but that can be something that dupes us. Don't be intimidated by a particle diagram. We have seen them several times. All right, and again, the important thing there is the relative number of particles. That is always something that is deliberate. And don't worry about boiling, freezing point depressions. You're not going to have to do those calculations. So it's something that I wouldn't spend any time on. All right, so that is our solutions. And in our last video, we will be talking about the photoelectron spectroscopy and some of those last pieces, Beer's law, things like that.